So in today's lecture we will see the digital protection, the portion which is widely utilized in today's scenario. So in case of digital protection, today we will discuss about the sampling and analyzing issues. So just move on to that particular slide. So as we all are aware of the fact that the signals used in the power systems are basically analogous in nature. The voltage signal or either the current signals, they are analogous in nature. While for digital protection, or we can say in case of computerized protection, the signals which are used are digital in nature. So the process of converting those analogous signals into digital signals are basically termed as sampling. So how it is done and what are the how it is carried on is seen in this lecture. So sampling, again I will say that the signals we use in electrical power systems, which are voltage and current, are analogous signals. Now to process these signals into computers for digital protection, we need to convert the signals to digital form. When an analog signal is continuous in both time and amplitude, a digital signal is discrete. We can also say that we have to convert the signal into discretized form. So to convert a signal from continuous time to discretized time is called sampling. Now it is the process of measuring the instantaneous value of continuous time signal in discrete form. Now a piece of information from the whole that is continuous in time domain is called a sample. We will see soon what is sample. Now sampling can be defined as the discretization of an analog signal which is generated at the source. Now this is considered, if this is my continuous signal xt, so this is my discretized signal. Now this is known as the sample. The time gap between these two samples is known as sample time. So the below diagram illustrates a continuous signal x of t and a sampled signal xs of t. Now it is obtained when xt is multiplied by a periodic pulse train. Fine. Now what is sampling rate? Now the gap between the signals after discretizing the signal is called sampling period. This gap between these two signals is known as sampling period. Now sampling frequency is 1 by Ts of sampling time, where Ts is the sampling time, Fs is the sampling frequency or sampling rate. Now sampling frequency is the reverse or the reciprocal of the sampling period, also called as sampling rate. It represents the number of samples taken per second. Now to reconstruct a digital signal, or we can say to construct a digital signal from analog signal, the sampling rate should be taken into account. Now the sampling rate should be calculated such that the signal should neither lost or overlap. For this purpose, a rate was fixed which is known as Nyquist rate. So what is this Nyquist rate? Now consider a signal which is band limit with no frequency components greater than W Hertz, which means W is the highest frequency of that signal. Now for the reproducing the original signal, the sampling rate must be twice the highest frequency. We will soon see in the sampling theorem the same concept was utilized. Now where Fs is the sampling rate, W is the highest frequency. Now the rate of sampling is termed as sampling rate. Now this is sampling theorem. Now this theorem states that the signal can exactly be regenerated or reproduced if its sampling rate Fs is greater than twice the maximum frequency, that is twice the Nyquist criteria. We have seen that. Now to clearly know about the sampling theorem, now take a signal. This is the signal whose magnitude greater than W is 0. Okay. This signal is ultimately the frequency domain signal of time domain signal xt that we have seen previously. Now, even after sampling, we need a sampling frequency for having no loss of information. Now, the Nyquist rate is the one which is 2 times the maximum frequency that we have seen. Now, that means if the signal xt is sampled above the Nyquist rate, then the original signal is regenerated. If it's sampled below the Nyquist rate, the signal is lost. Now the diagram shows that if the signal is sampled at higher than 2W, which is the Nyquist rate in the frequency domain, then we will see that the signals are clearly separated by each other and there is no mix-up of signal, as there is no recovery, and at the same time recovery is easy and it is very much possible. Now see, now the Fourier transform of the signal xs of t is 1 by ts summation n raised to power minus infinity to infinity x of s omega minus n omega 0, where ts is the sampling period and omega 0 is equals to 2 pi upon ts. Now suppose the sampling rate is equals to twice the highest frequency 2w. In the previous case we have seen that the sampling frequency is greater than the peak frequency. Now in this case we are seeing the sampling frequency is equal to twice the highest frequency. So this is the resultant diagram. In the previous we have seen that previous diagram that both the signals are separated by a particular gap, but now in this, when the frequency is equals to the sampling frequency, highest frequency is equals to the sampling rate, then there is no gap. This is the data is replaced without any loss. It is considered to be a good sampling rate. Fine. Now let us see when the sampling rate is less than twice the highest frequency. Now in this case we will see that there is an overlap of the two signals in this point. So from the above pattern, the overlapping of data is seen, leading to mixing up and loss of information. This phenomena of overlapping is called aliasing. Fine. Now we will see what is aliasing. Aliasing is the presence of unwanted components in the reconstructed signal. Now these components were not present when the original signal was sampled. Now in addition, some of the frequency in the original signal may be lost in the reconstructed signal. Now aliasing occurs because the signal frequency can overlap, as we have seen, where the sampling rate is less than the highest frequency, there is an overlapping of the signal. Now if the sampling frequency is too low, the frequencies fold around half the sampling frequency, which is why these frequencies often referred to as folding frequency. Now, aliasing can be defined as the phenomena of higher frequency component in the spectrum of a signal taking on the identity of lower frequency component in the spectrum of its sampled version. Now, how can we reduce this aliasing effect? Now, low pass anti-aliasing filter is employed in the transmitter section of pulse code modulation before the sampler to remove the high frequency component that are not required. Fine. The signal obtained after filtering is sampled at a rate which is slightly higher than the Nyquist rate for the easily reconstruction of the filter at the receiving end. So this is how we can convert an analog signal into a discretized signal for the purpose of computer relaying. Okay, thank you.